Hello and welcome to the 8th video in this video series on fields in physics. Today is really going to be a summary video of the concepts in which we have been discussing, so comparing gravity and electrostatics. Now, here is a thought for you, courtesy of Michelangelo's painting of the creation of Adam. Here we have God and Adam, fingers almost touching. Adam has fallen to earth with the weight of humanity on his shoulders, the apple synonymous with Adam, Newton, and gravity. And then there's God, powerful like lightning. Stories of Zeus's thunderbolt. He is definitely a force acting at a distance. His presence is much like the mystique and magic of electricity. So, whoever thought religion and science were different ideas, or opposing ideas for that matter? Okay, let's get back to some physics, and we'll start with point field diagrams. Specifically, we're going to look at force, field strength, potential energy, and potential diagrams. So as in clarifying this concept, as the distance r gets greater, we can see this person moving further and further out, force and field strength decrease by a factor of 1 on r squared. Until that force actually becomes 0, infinitely far away. So the force due to gravity is 0 at infinity. Similarly, the potential energy and potential increase, but as we get further away, there's a slower and slower rate. And at 0, we go from a negative potential up to a 0 potential. Now, let's have a look at all of these 4 graphs. So in summary, we've done this in previous videos, but the force diagram, if we add up all those areas of force times the little rectangles against radius, we have the area under the curve, which is actually the integral of the force dr there. Oppositely, and that will give us the potential energy graph. Oppositely, the slope of the potential energy graph will give us the force. So as you can see, the slope is decreasing or becoming flatter, and so the force is becoming less and less steep, as you can see there. Now, similarly on the right, there is exactly the same scenario here. The field strength, represented by either the force per mass or force per charge, the area under the curve of the field strength diagram will be represented as the potential diagram. And similarly, the slope of the potential diagram will be the field strength diagram in terms of the y positions there. Okay, let's look at gravity. The formulas here in summary. The force of gravity is gmm on r squared. Now to go to field strength, we need it per mass. So dividing it by mass there, we get g as being little g as being the gravitational field strength, which is gm on r squared. Now we can think about this in the same sense. Going from potential energy of gravity, we have minus gm m on r. Now going from potential energy to potential, it's per mass or on 1 kilo. So the potential of gravity is minus gm on r. Okay. Now let's look at electrostatics, or electricity should I say, and the force electrostatic or electricity force is kqq on r squared. Now this is per charge or per little q divided by little q. We have E being the electric field strength is kq on r squared. Similarly here, the potential energy electrostatic is going to be minus, I'll put a bracket minus here because it could be positive for like charges, minus kq, little q on r, which is almost the same formula there as the gravity one, and it's going to be per charge to get from potential energy to potential. So we have VE equals minus KQ on R. Now the reason I put the bracket minus there is the shape of the graph for a like charges. So for a set of like charges which have a repulsive force, we'll have a potential energy diagram as such there. Okay, and if we have a look at opposite charges, they are attractive force, so they'll have a similar diagram as the gravity type graph there. So it's important to note the differences there. Just note with the force and the field strength, we're only using the magnitude of those forces. Okay, let's go to a fun fact. This one's about the sun, and the gravitational field strength of the sun at its surface, should I say, is 275 newtons per kilo. So after just 1 second, you'd actually speed up by 1,000 kilometers per hour. That's assuming we wouldn't get burnt up by the sun's surface, or if there was no air resistance as well. But that is a massive acceleration due to gravity and gravitational field strength that you would feel on the surface of the sun. Okay, let's have a look at uniform field diagrams, and we're going to do this in a similar manner to point field diagrams. Now, as you can see, as a summary, the area under a force curve gives us potential energy, the area under field strength graph gives us potential, and vice versa. The slope of the PE graph will give us the force, and the slope of the potential graph will give us the field strength. As you can see, it's a linear graph for potential energy and potential, and a constant graph for force and field strength. Let's go through gravity first of all. So the formulas here, so we have force equals mg, and mg will be constant in this particular case because g is a constant. Now it's per mass, so we actually just get divided by m, and we just get g being a constant. So for example, on the surface of the earth, it's 9.8 newtons per kilo. Okay, now the potential energy is going to be the slope of that graph, okay, or the change in potential energy will be mgh. And for the potential graph, we're going to divide by m, and we get the change in potential will be GH. Now, those graphs could have different directions purely because it's a linear graph and the magnitude might be negative. Okay, let's go through electricity. So force is charge times the electric field strength, and if we divide by Q, the electric field strength will be a constant. Looking at potential energy, the change in potential energy in electrostatics is going to be QED. And it's per charge to get to voltage or potential difference. And so the potential difference or change in potential is ED there. Okay, and that's a good summary of all the formulas for uniform fields. Okay, in this next example, we are going to do a proton force comparison. So what we're going to do is it's going to be gravity versus electricity. So the gravity between two protons at a distance of 1 meter versus the electrostatic force separated by 1 meter. Okay, so the mass of a proton we're going to use as big MP and also little MP, and QP for, not QP mayonnaise, but the charge on a proton is the electrostatic charge there. Okay, so we've got the mass of the proton, which is 1.67 times 10 to the minus 27 kilos. It's very light, it's not very big. The charge on a proton is, let's have a look here, 1.6 times 10 to the minus 19 coulombs. And we'll wait for the coulombs here. It's exactly the same charge as an electron, so we know that the charges of a proton and electron should cancel. Okay, we're going to use big M and little m as the same, being the same masses. So we're going to go force of gravity is gmm on r squared. And we're going to assume the distance between them is 1 meter just for brevity. So putting this in our formula here, we have the gravitational constant times the masses squared on 1 squared, and we have a tiny force of 1.86 times 10 to the minus 64 newtons. That is minuscule. That is really tiny. So now let's go to the electrostatic force between a proton separated by 1 meter. So K is a lot bigger, 9 times 10 to the 9, times it by the charge of a proton squared, divided by 1 squared, the distance 1 meter. And we get the force electrostatic is 2.3 times 10 to the minus 28 newtons. Now, that just means if we compare those forces with this example, it is 1.23 times 10 to the 36 times stronger if we're comparing protons. So 1.23 trillion times stronger. So this means that electricity wins in the proton comparison there. Well done, electricity. You're trillion times stronger there. Thank you for watching today's video. This is the final video comparing gravitational and electrostatics. Definitely subscribe to these videos, and please definitely put some questions that you've got around this whole topic of gravitational versus electrostatics. And thank you for watching.